class period. That's all right. All right. What questions do you have? Things are going okay? All right. Well, last time we finished up talking about vector spaces. Well, not vector spaces. We talked about Euclidean vector spaces, RNs. Talked about some different properties that those vector spaces have under what we typically refer to as ordinary addition and ordinary scalar multiplication. Today we're going to abstract the notion of what we mean by a vector space, treating other objects besides. That's from last time. If you already had that, Matt, I don't know if you had that one or not. Okay. We're going to abstract the notion of what we mean by a vector space, treating other things like vectors. Perhaps any continuous function might be a vector. Any differentiable function might be a vector. Polynomials might be your vectors. We're going to abstract the notion of what we mean by vectors, have a list of properties that all vector spaces have to satisfy, and then check those properties and see if we have vector spaces or not. Before we do that, though, the concept of linear combination is going to pop up a lot. We've already seen this idea for linear combination when we talked about writing solutions of systems of equations in parametric form. So just a reminder of that. If you had, say you had the homogeneous system where you did your reduced row echelon form look like the following. Say that you had a homogeneous system of equations, you row reduced, and got this as your matrix in reduced row echelon form. And I want to write the solutions. Okay. How many variables are we talking about? That's from last time, by the way. You already had those from last time. Okay. You did not have those from last time. All right. How many free variables do you see? 2? Good. So that would be your x2 and your x5, right? So refer to those as parameters s and t. Nope, sorry, x4. Sorry, that's x4. Yep. x5 is equal to 0. x3 is equal to negative 2t, and x1 is equal to, yeah, so negative s plus 2t. And then we also talked about how we can write that in parametric form. We've got something that's multiplied by the s and something else that's multiplied by the t, right? In this case, what's multiplied by the s? Good. And the other one? Good. So notice every single solution can be written in terms of the vectors negative 1, 1, 0, 0, 0, and 2, 0, negative 2, 1, 0, right? We can change anything we want for the s, anything we want for the t as far as constants goes, but every single solution is sum of multiples of those two vectors, right? So what we say is that these solutions are the set of linear combinations of those two vectors, and that's exactly what we mean by a linear combination. So as far as the definition goes, when we have a linear combination of v1 out to vk, this is going to be c1 v1 plus c2 v2 plus cn vk or ck vk, where each of your constants are, in this case, real numbers. It's possible that in other vector spaces, your constants may be coming from a different algebraic structure. One of the more common ones would be a field, would be the complex numbers. In general, your constants have to come from what we mean by a field, an algebraic structure referred to as a field. It sounds weird, but field just means that we can add, subtract, multiply, and divide, as long as you're not dividing by 0. Basically what a field is from an algebraic expressor standpoint. So your complex numbers would satisfy that. Your rational numbers would satisfy that. But there's a bunch of other examples of fields. We're going to do what we refer to as real vector spaces, so our constants will come from the real numbers. Our scalars will come from the real numbers. But this is all we mean by a linear combination. We can, that's from last time, wasn't it? We can multiply each of the vectors by a constant and then add up all those things together. One of the things that we're going for, and just to try to keep this in mind as we go forward, is this idea for what we did with the solutions. I can write every single solution of this particular system of equations as a linear combination of two vectors. I can write it in terms of two things. Okay? So I can describe infinitely many solutions with two things. This is kind of a goal. All right? So keep that in mind going forward. That's what we're trying to head toward. Okay. All right. But let's do a little bit more of a straightforward example here. So just make sure we have a feel for what we mean by linear combination. We want to write this vector x as a linear combination of the v1, v2, v3. So without worrying about what the numbers are, this just means that we're trying to find constants c1, c2, and c3 so that when we do the c1, v1 plus c2, v2 plus a c3, v3, we get that vector x. That's what it means, right? It says write x as a linear combination. We just have the definition of linear combination, right? Constant times the first vector, constant times the second vector, constant times the third vector, add them up. Okay? Doesn't matter what the vectors are, that's what that means. Okay? Now let's see if we can put in the the values here. And I know that I've got my vectors written horizontally, but I'm going to write them vertically on purpose, and hopefully we'll see why here in a second. Okay? So I need C1 times 1, 3, 5 plus C2 times 2, negative 1, 3 plus C3 times negative 3, 2, negative 4 to equal negative 1, 7, 2. This is what we're trying to solve, right? We need to find C1, find C2, find C3 if we can, so that that equation is true. If that equation, that vector equation is going to be true, can you give me one equation that has to be true just involving numbers and variables?
C1 plus 2C2 minus 3C3 plus negative 1.
Okay. And how'd you get that one?
The top row.
Good. We're just equating those top components, right? What would the second equation be? You're fine.
Then 2C2 plus 2C3 equals 7.
Good. And you got that by looking at what?
Multiplying the constant by 7.
Good. Yeah, we're just doing that second components right across that way. And then hopefully you can see we can do the same thing in the third component. Pardon me, goodness. And get the 5C1 minus 3C2 minus 4C3 equals 2. Now you've set up a system of equations. What's our big method for solving a system of equations? Make a matrix and row reduce, right? Okay, so notice, and this is why I wrote them in columns to start with, by the way. My first column will be 1, 3, 5. My second column will be 2, negative 1, negative 3. My third column will be negative 3, 2, negative 4. And the fourth column will be negative 1, 7, 2. Notice that the columns of the matrix that we just formed from this system of equations is the same as if I would have just taken my 3 vectors to start with and pop them in columns, and then put my fourth vector and put it as the column on the end. Yeah, I don't think it's... Oh, yep, it's positive. You're right. Thanks. Who put a negative there? Okay, so I went through writing the equation down here, getting the system of equations and converting it over, but we could have just started by putting the vectors as columns in your matrix and been done. That was why we wrote it as a column form to start with, to see what the correlation was in.
For future reference, would you want us to write the equation?
Nope.
Just go straight to
You can
it?
just go straight to this. Yep. Yeah, that's kind of the point. Yep, I just want to go straight to that. Yep, good. And then you would row reduce. So who wants to do that on your calculator? Yes. No, I want you to use your calculator at this point. I'm not going to ask you to do this by hand. I want you to use your calculator and put it in reduced row echelon form immediately. Please do not do it by hand. I'm not saying knowing how to row reduce is unimportant. It is important. What I'm saying is that we want to use the technology tools to help us get this done so we don't keep doing it over and over again.
Like 1, 0, 1, 7, 0.
Say it again.
It gives a not true statement.
Okay, that's fine. Well, what do we get for the reduced row echelon form? Was it 101 across?
I got 1, 7. 1, 0, 1, 7, 0.
Say it again.
1, 0, 1, 7.
The 7 here?
7. I got 1 over 7.
A 1 over a 7. That's what you're telling me. I'm sorry. And then
0.
0. Okay.
0, 1. Maybe 11 over 7. 0.
Okay.
And 0, 0, 0.
Good. Good. Is that what others got? Okay. I thought you were telling me 5 columns. I was very confused. Yeah, 1/7 is what you're saying. I thought you were saying 1 and then 7. I apologize. I just misunderstood. All right. What does that last row tell you? Good. It tells you it's inconsistent, right? It's not possible. So what does that tell us about the original problem? Notice it said we express it as a linear combination if possible, right? So what would you tell me? It's not possible. Yeah, it's impossible. Good. So again, this last row, again, for the system of equations, tells us inconsistent. So X is not a linear combination of your V1, V2, V3. That okay? Right. Tell me how to set up the next example.
The first column would be 2, -3, -6.
Careful. Yeah, 2, the first column 2, 1, 1, 2, right? We're going to write our vectors vertically. Second column will be
-3, 3, 4, -5.
okay.
-6, 3, 1.
Okay.
7, 2, 5.
Good.
One, 0, 0, 2. 0, 1, 0, 1. 0, 0, 1, -1. Then row zeros.
Okay, good. that row of zeros causing us any problems here? No. Okay, remember again, these right here are referring to those constants that we would have, right? This would be your C1, your C2, your C3, right? So if I've got my 7, 2, 5, negative 3 on the right-hand side, what would you multiply the 2, 1, 1, 2 by? 2, good. What would you multiply the negative 3, 3, 4, negative 5 by? 1. And what would you multiply the negative 6, 3, 1, 2 by? Negative 1, yeah. Right, because we're trying to find C1 V1 plus C2 V2 plus C3 V3 equals X. This is C1 C2 C3. Yeah, that one.
Would we be able to write our answer vertically like we did?
You can absolutely write it vertically. I just wrote it horizontally here just to match with the problem stated. But you can absolutely write it vertically. That's not a problem. Are we okay with where those numbers are coming from for the constants? And you can check your answers too, right? One of the nice things is I can check my answers pretty quickly. You get 4 minus 3 plus 6 gives me 7. 2 plus 3 minus 3 gives me 2, and so on down the line. Okay? We're going to do more with linear combination. So if it's still a little fuzzy, that's okay. We're going to do more with it as we go through, well, the next several sections. Not necessarily the next one, but as we go through several sections for the rest of the semester, we will be talking about linear combination. All right, so we've talked about vectors in Rn and different properties. Now it's time to get a little weird and abstract some things. Because that's what mathematicians do to you, don't they? One of my former colleagues at former school said, a lot of students think of mathematicians as basically trying to play a game with a 5-year-old. So as you try to figure out the game, they change the rules on you. Okay. That's what we're going to do today. We're going to change the rules. Yeah.
So visually speaking, when you want X is the vector that's the result of V1, V2, V3.
Yeah.
As it the only result. In other words,
You mean the only way to do it? Or?
No. It's the only answer. In other words, if you add those three vectors together, you're going to get 7, 2, 5. If you use those constants, yes. Yep. It might be the case that you've got, sorry about that. It might be the case that you've got several different ways that you can do it. It may not necessarily be unique. Depends on which vectors you start with. And we're going to do that more later as well. We would like it to be unique, right? We'd like a single answer. Sometimes we may not get a single answer. So that's stuff that we're headed to later. Yeah, of course it is. I always push it off to later. I did that a lot last semester when I was teaching my abstract algebra class. It was, for weeks, it was, we'll do it later. And then it was a hell of the last 2 weeks of class. After we put everything back together again. All right, so this section talks about, a lot of books will call these abstract vector spaces. Basically, all we're doing is just, the abstraction part is, we're going to let anything be a vector that we want, as long as we have operations defined and they behave with each other nicely. Okay? So we talked a little bit about what we mean by behaving with each other nicely. When we did all those properties that the Euclidean vector spaces have, right? For example, scalar multiplication has to behave nicely with respect to addition by distribution across it, right? It's one of the things I mean by behaving together nicely. All right, so let's go through the definition, go through the properties, and then start looking at some of these abstract ideas. So notice I'm saying we can use anything we like as a vector. So the first thing that we start with is that we have some non-empty set to start with. Okay. I mean, we have to have vectors. That's why we're saying non-empty set. Okay. We have to have some vectors in there.
We also need two ways to describe how we're going to combine things. So we have two binary operations. That's all binary operation means is you're going to take two things and combine them together. Okay. One of them, we use the names scalar addition and scalar multiplication. The addition and the scalar multiplication don't have to look like normal. Okay. They can be weirdly defined. Right. This is the name we give. But addition is a way to combine two vectors. Scalar multiplication is a way to combine a number in a vector. Okay. Binary operation just means it takes two things to put together. Okay. Not everything is a binary operation. Sometimes you have what's referred to as a unary operation. For example, do negation. That's a unary operation, right? You put one thing in, and then you take the negative of it. That's a unary operation. Okay. You can have ternary operations. For example, if you did Calc 3, one of the things that you might have talked about was being able to, when we talked about it earlier, but talk about doing what's referred to as the scalar triple product, where you end up taking a determinant of three vectors. You put in three vectors and then do that determinant. It gives you the volume of the parallelepiped. Okay? That would be an example of a ternary operation. I put three things in, I get an answer. Okay? If you do computer science, you do functions, right? You pass things through your function and you get an answer out. The number of things that you pass through would be that type of operation. So if you've got two things going through, that's a binary operation. If you have three things passed into the function, that'd be a ternary operation, and so on up the line. Okay. Anyway, that's all we mean by binary operations. You put two things in and combine them somehow and get an answer. Okay. All right. What we mean by what we refer to as a real vector space, and it doesn't mean real as in it exists. I know it sounds weird. The real part, this just refers to the fact that our scalars are real numbers. I could write where you could actually read it. Okay, that's all the real part means. It's just telling you where the scalars are coming from. So if your scalars were complex numbers, this would be a complex vector space, and so on. So that's all the real part means. It doesn't mean that they exist. They all exist. It's just telling you where the scalars come from. All right. So we refer to V as a real vector space, or we'll just say vector space, if we find out that all of these following axioms hold. These axioms are going to correspond to those 10 things that we wrote down that Euclidean vector spaces have, those properties. Okay. So the first one is that closure property. If I add, however addition is defined, if I add U and V together, I land back in my vector space again. So this is closure under addition. Yes? I mean that when you add the two things together, you get an answer that is in the set that you started with. So let me give you an example. Start with the positive integers and do subtraction. If I subtract any two positive integers, do I always get a positive integer back? If I take 2 minus 3, do I get a positive? No. So that's not closed. It did not land back in the same set I started with. If I say you have to start in the positive integers in my operation of subtraction, then it's not closed because my answer didn't land on the same spot. Okay. All right. We want our addition to be well-defined, or not well-defined, nicely behaved with a couple of respects. One of them is commutativity. And it's T's. It's commutative, like you're going back and forth to work. It's not communicative. You're not diseased. is not commutative, you're not a hippie. Okay? It's commutative. T's. Commutativity, yes. Okay. I hear communitive a lot. It drives me crazy. I'm a commutative algebraist, so that's why it drives me nuts. Okay. All right. Anyway, closure under addition, commutativity of addition. The next one's associativity. Oops. Again, these first two properties are properties that you would expect an addition to have, right? Being able to add in either order, being able to regroup. And again, think about, in particular, thinking about the regrouping part. This is a property that you would like in order to be able to solve equations. Remember, algebra has its roots in solving equations, right? The whole point. Okay. Remember, we talked a little bit about this last time. If you have x plus 3 equals 9, the first thing I have to do is, of course, subtract 3, and I need to know what I mean by subtraction. But notice the reason why you subtract the 3 is because you're trying to get rid of that plus 3, right? But right now they're not grouped in the right spot, right? So in order to be able to cancel those things actually out, I need to regroup, right? That's why associativity is important. I need to be able to do that to be able to solve that equation. Okay. If I didn't have associativity, I wouldn't be able to go from here to here and I'd be stuck. Okay. Now, why did we add negative 3 in this case? We added the negative 3 because I'm trying to make this what? 0, which means I better have some sort of a 0 vector, right? So there exists something that we call the 0 vector, so that when I take any vector, oops, let's actually flip my order here. Not E, 0, U. All right, so there exists a vector 0 that when I add it to anything, I just get that anything back again, right? Now this, by the way, this is important for some of the things about whether or not you think it's a vector space. The 0 vector cannot change depending on what other vector you're using. The exact same vector has to work for every single vector in your vector space. Okay? It does, your 0 vector does not get to change. Okay? It stays the same all the time. All right. It also, again, notice it depends on what the operation is. It depends on what your addition is. I mentioned this last time, but just to reemphasize. If for some reason you defined addition as multiplication, what would your 0 vector be? It'd be a 1, right? It had to be 1s, correct? Okay. Okay, so be careful with that. Your 0 vector is dependent on what you're calling addition. Just because I'm saying the word addition doesn't mean we're adding. That's just the name we're giving for the operation. Okay? It's entirely possible we define addition as multiplication. Okay? If you're saying by addition, I really mean multiplication, then the 0 vector is 1, not 0. Because it's the thing that has to leave it alone when you do the operation. And multiplication by 1 leaves it unchanged. That's what I mean. So what this part here is existence of a 0 vector. Okay. I know some of the stuff that I'm saying is weird, and we're going to do some weird examples, and then we'll go back to normal examples after we're done, basically. Okay. All right. Why did we want a zero vector? Well, it's at this stage where I've got the x plus 0 idea, right? I need the plus 0 to go away. But remember, to get to here, I had to do the inverses, right? So once we have a zero vector, we can also talk about the idea of additive inverses. So for each vector in V, there exists something we'll call the negative, the negative of U in V, so that when I add my U to my negative U in either order, I get the zero vector out. Okay.
Now, I mentioned a minute ago, this zero vector cannot change for anything, any vector that you use, right? Whenever I add it to 0, I get that vector back. That vector has to stay the same all the time, right? And think about that, right? When I add 0 to any number, that 0 number doesn't change at all, right? However, when I do an inverse, the inverse does depend on the vector that you start with, right? Under real number addition, the inverse of 3 is negative 3. The inverse of 2 is negative 2, right? It changes depending on what you started with. Okay. What I'm saying, though, is that the zero vector cannot change. Your inverses will change depending on what you start with, but the zero vector is the zero vector, 1. Okay. So we've got 5 axioms here that deal with addition. The next 5 deal with scalar multiplication. If I multiply by a constant, I get back in my vector space. So this is another closure axiom. If, to give you a specific example of something that would not be closed here, let's say that as your vectors, you're saying, make them two-dimensional, but you only allow rational coordinates, only fractions. To be a real vector space, your scalars are any real number, right? If I take a rational number and multiply it by any real number, am I guaranteed to get a rational number back again? No. For example, I take 1 times the square root of 2. That's a mess, isn't it? It's not rational anymore. Okay? So that's an example of something that would not be closed. If I said my vectors are two-dimensional vectors with rational components, then it's not going to be closed under scalar multiplication. Okay? I could also say, what if I said two-dimensional vectors where I only allowed positive coordinates? What would I multiply by and make it not closed? Anything negative, right? All right, so there are some examples for you for things that aren't closed under scalar multiplication. Pardon me. The next 2 are, let me do the order that way, same way they have in the book. I think the next ones are the distributive ones, but yeah, they are. Okay, good. I just want to make sure I write it in the same order if you look at the book. If I take my C, my constant, and multiply it by a sum, what would you like that C to do? Yeah, distributed to both of them, good. Or if I add my 2 scalars and then multiply, you'd also like that to distribute, wouldn't you? Okay. Notice, I mentioned this the other day, but I'm going to mention it again because it's important, especially in the second one here. On the right-hand side, what kind of objects are you adding together? Vectors, right? When I do a scalar times a vector, I get a vector. Scalar times a vector, I get a vector. I add two vectors, I get a vector. Right? What kind of objects am I adding here? Constant scalars, right? When I add two scalars together, what kind of a thing do I get? A scalar. This plus sign right here represents regular old real number addition. That's not weird. That's not a weird addition ever here. Okay? If I'm adding two numbers together, you're going to add those two numbers together like you always add those two numbers together. Okay? The only time addition can get weird is if I'm adding two vectors together. Okay? So that's important. So especially this one is saying something, right? I'm adding two different types of objects, but I'm saying it doesn't matter if I add these objects together first and then multiply, or multiply and then add two different types of objects together. I have to get to the same place. Okay? All right. Last two, we're almost done. This is also saying something. If I have my CD and then times U, that's the same as C times DU. This is an associativity property. If I could spell associativity, that would be helpful. I am having one heck of a time spelling today. There we go. Again, just like the previous one, this is saying something. What kind of objects am I multiplying together here? Those are real numbers. So this is regular old real number multiplication, not weird multiplication. Okay? What kind of an object is D times U? A vector. So that's a vector, a scalar multiplication of a vector, right? That could be a weird multiplication. So again, we're saying that we're able to change where the multiplication is and still get the same answer. All right, last one. Was that one? Your book refers to it as scalar identity. Basically, this leaves your scale alone, right? If I take it, basically this last one says that scalar multiplication does what you would expect it to do. It's talking about changing the length of things, right? So if I multiply by 1, it shouldn't change its length. It's not quite what it's doing, but that's kind of what the way to think about it, right? When you say scalar multiplication, you're thinking of changing the scale, right? Well, you would assume that your scalar multiplication, if I multiply by 1, shouldn't change your scale at all. That's what this last one is saying. Okay. All right. So let's see if we can do some stranger examples. But before we do stranger examples, let's talk about some common examples. These are ones that we will deal with as we go through. So first one we've already talked about, right? The RNs, those are your Euclidean vector spaces, Euclidean n space. We just talked about those in the last section, section 4.1. We already went through all those properties there, right? M sub mn is your set of m by n matrices. Oops. Notice here we're saying under ordinary matrix addition and scalar multiplication. What we mean by that is, how do you add two matrices together? Yeah, just add the entries together, right? Does that change the size of the matrix at all? No. So you add two matrices together, you get another matrix of the same size, it lands back in that space again. Okay? What do you do when you do scalar multiplication for matrices? You multiply every single entry by that scalar, right? Same thing, lands back in there, right? So that's both closed, correct? That's both closure properties, right?
I add two things together, I get something back that looks the same. Multiply by a scalar, I get something that looks the same, right? Okay. We've already proven, way back when we did matrix arithmetic, that our matrix addition satisfies all of those axioms, right? And we also talked about how scalar multiplication works, correct? So we know that the 10 axioms are satisfied by our matrix arithmetic properties. Why am I having such a trouble with the phone? I don't know what is wrong with my spelling today. Having issues. We've already talked about those matrix arithmetic properties, right? So those all work, so those all satisfy those identities. Notice we did matrix addition and scalar multiplication for closure. Would the set of m by n matrices, if I said make your addition multiplication, would that work? Well, first, in order to make it work and be closed, what would have to be true about m and n? They'd have to be the same. They'd be square, right? Because I can't do an m by n times an m by n unless my m and n are equal, correct? So first they have to be square, correct? Even if they were square, would it work? What doesn't work? Multiplication doesn't work because why? The commutative property. Good. Yeah, multiplication won't work because I can't multiply in either order and get the same answer, right? So I can't define addition as multiplication for matrices and still keep a vector space because it doesn't have the right properties. Okay? So it's important to make sure those properties are working. So in this case, ordinary, just fine, right? Ordinary addition, ordinary scalar multiplication, we're good. If they change either of those things on here, you're going to have to check it. Okay? All right. Another important one that we'll talk about is the set of polynomials of degree n or less. Now let's say why we have to do, well, you know how to add polynomials, right? Notice that you add them term-wise, almost like it's component-wise for vectors, isn't it? Keep the constant terms together, keep the x terms together, keep the x squared terms together, right? So on and so forth. Basically, when you add polynomials under the normal way or scalar multiplication, it's the same as doing your Euclidean vectors. Okay? Multiplication gets strange, right? Multiplication's weird for polynomials, but addition, scalar multiplication, you're good. Okay? All right. Why do I say degree n or less? Why do I need the or less part here? Why can't I just say polynomials of degree 2?
Because a polynomial always starts with the highest degree and goes down.
Okay, it certainly starts with a high. Well, if you think about it with your highest degrees. Say it again. Okay, so what would happen if it? How could you make something start with a 0? Think about closure. If I said that everything had to have degree 2, would it be closed necessarily under addition? Can I add something to x squared and make the degree go down? Okay, good. Can you give me an example? It's probably yes if I'm making a big deal out of it. I can do a negative x squared and maybe put an x on the end, right? What's the degree of that? Ah, there we go. Good. Notice the degree went down, right? In order to make it closed, it's necessary to have this part. It's necessary to make sure that we say or less. Okay? We need to make sure we say the or less part because we can cancel off like terms, right? And make the degree drop. Okay. Now, what about the last part here? Why is this little parenthetical in here? This is more of a technical thing than anything else. Degree of a constant polynomial is what? What's the highest power of x you see in a constant polynomial? 2. Constant polynomial. No x's in it. No x's in it. 0. There we go. Yeah, degree 1 has to have an x in it, right? Degree of a constant polynomial is 0, except for one constant polynomial in particular. If your polynomial is just the 0 polynomial, what's the highest power of x you see in that polynomial? I don't see an x, right? So I can think of it as x to the anything, right? So the 0 polynomial has no degree. That's why I have to put that extra little thing in there. Oops. It's not degree 0. It has no degree. Maybe back in high school when you learned about slopes of lines, you talked about the difference between slope equal to 0 and no slope. No slope means a vertical line. Slope equals 0 means a horizontal line. Okay? Same kind of concept here. Degree 0 is different than no degree. Okay? That's why we have to say put the 0 polynomial in there as well. I need the 0 polynomial because I need a 0 vector, but I can't define the 0 polynomial in terms of degree. Okay. So in any event, that's the important part of that part. Anyway, just wanted to mention that. Set of functions that are continuous under ordinary function addition and scalar multiplication also works. Notice your notation here. This is the big thing. When I put the C out in front here, this is standing for continuous functions. This A to B here is talking about your domain of that function. Okay, or at least what interval that you're looking at. Okay, so continuous functions on the interval from A to B. What type of calculus operation might you be interested in doing if I'm saying the function needs to be continuous to start with? Integrals, right? If we know we start with a continuous function, we know the integral exists. Okay, so there'll be a special type of product that we'll talk about for integrable functions that will work in terms of integration, I should say, that'll work because we're doing continuous functions. Okay, just as another notation here to go along with this, if you put a number here that looks like an exponent, usually this will be an open interval then. If you put a number there that looks like an exponent, this is talking about functions that are n times differentiable on the interval from A to B. And then if you put an infinity sign up there, that means infinitely differentiable. Oops. Okay. So to give you something that's maybe 1 times differentiable, but not 2 times differentiable, maybe you do something like f of x equals x to the 4/3. Is there any bad numbers to plug in for the derivative of that one? Or is that okay? Can I plug anything I want in for x there? Yeah, that's okay. But what happens when I take the second derivative? What is your x? Oops, forgot my third in the denominator, didn't I? What happens when you take the second derivative? Is there something that I cannot plug in there now? 0, right? So in this case, you would say that f of x equals x to the 1/3 is in maybe C1, negative infinity to infinity, but not in C2, negative infinity to infinity. Okay. I can differentiate x, not 1/3, 4/3. I can differentiate x to the 4/3 anywhere I want, but I can't do the second derivative at 0. That's what that says. Okay. So it's 1 time differentiable, but not 2 times differentiable everywhere. Okay. All right. So those are some common vector spaces. We'll do some stranger examples next time. We'll do that on Wednesday. I do want to hand out a homework in case you're interested in homework. If not, you'll have it for practice. Otherwise, we'll do more of these next time. Have a good one. See you on Wednesday. Good to see you back. I was a little worried.
Well, no, I had a.
Oh, gotcha. Oh, probably not. I figured something was up. Say that again.
Video.
Oh, good, good, good.